Exercise 3 is very similar to exercise 2 with one simple exception, and that's part A. So I'm going to help you through part A, and then I'm going to give you the opportunity to pause and try part B, C, and so on by yourselves to come back and check. So as always, reading through this thing, we see 3 different percents, and then we have a probability we're looking for. So let's go ahead and translate what it is we've been given and what we want. So we have this 48%, we have a 53%, and by the way, this is exactly how the worksheet is set up for this week, is having all of these sort of blanks and you have to fill them in, and I do give points for these, so if you get them wrong, you will lose points. All right, so do a quick read through. It looks like we're talking about laptop and desktop computers. Yeah. And we're talking about students in every single situation. So students is just our population. We don't have to worry about that. So reading through, we see college students have laptops and separate information, right? 43% have desktops. So 2 separate thoughts there. So we've got just laptop here, desktop here. And at the end, they even told us use L for laptop and D for desktop. So even if we hadn't read carefully, they would have told us what those events were. And then we have the most important sentence, one that gives us the hardest thing usually to translate. 79% of college students have a laptop or, oh, that one wasn't hard, L or D. Cool. And if we look, part A says, what is the probability a student selected has both a laptop and a desktop? So the hardest type of translation, the conditional, we haven't seen yet in this question. But this is still a challenging question in and of itself, because here's what students are going to do. And again, you can pause, try to think about how you would solve this. That would be ideal, right? But one thing you might do is you might go to your AND formulas. There are 2 different AND formulas we have. One that tells us if we have a given, then we can multiply by the thing we know, and one that tells us that we can just multiply the 2 probabilities together. Neither of these are going to help us here. The first one doesn't work because we don't have a conditional. And the second one is only true if they're independent. And there's nothing here to tell us that they're independent. So both of these are not going to be the way we solve this question. So what should we be doing instead? This is when, if you looked at the formulas on the test, you're going to sit there and go, turns out there is one more formula that helps us. Probability of A or B, and I'll just write it as L or D, is equal to the probability of L plus the probability of D minus the probability of L and D. So while it's not set up to solve for the and, it definitely can, right? In this case, we have the 2 things by themselves. We have the or. The only thing we don't have and that we want is the and. So this is just a basic algebra question. And I tell you with all seriousness, this is the hardest algebra you're going to have to do in statistics. So those of you who are not big math fans, here it is. We know L or D is 0.79. We know L is 48%. Probability of having a desktop is 53%. And look, we have an unknown. We can even make that X, right? So it looks very much like an algebra problem. And then we could even add these 2 together. 91 is equal to 0.79. And we do the hardest algebra you're going to have to see in this class. We're going to solve for this X, which means we've got to subtract that 91. And we get negative, oh God. My brain can't handle math like this at this point. I think it's negative 0.22 is equal to oh God, what happened? Is equal to negative X, which means X is equal to 0.22. So there you go. The hardest algebra you have to do in this particular class is solving for X in a very simple equation like that. So now that we have it, you should be able to fill in the contingency table. So I suggest you pause the video and try to do the rest of the steps of this problem by yourself, and then come back and see how you did. All right, so if you pause this, you should have gone ahead and put laptop, desktop, and our and in here, as well as our known 1. And then you could have filled in all the missing pieces based on the fact that we can sum down the rows and columns to our totals. So 47% didn't have a desktop, 52% didn't have a laptop. Again, this is obviously a dated question. We could fill in the rest of this, 27, 21, 31, and we can fill in the entire table so that everything adds up. Remember, down each of the rows, down each of the columns, everything should equal. Okay, the next thing asks you to fill in this Venn diagram. So remember, the Venn diagram is going to take the 4 ands of the contingency table, and it's going to convert them into the 4 parts of the Venn diagram. All right, so again, 22, this is laptop and desktop, right? We're in the L circle, we're in the D circle. Now, as we move over to any of the other places, now you can tell we're in the L circle, so this is L, but we're not in the D circle, so we are not in the D circle. So L, no desktop, this is 0.26. And there's no reason to label these. We can see it from the actual Venn diagram that's L and no D. And here we're in the D circle. We have a desktop, but we don't have a laptop, so this is 31. And then outside, you don't have a laptop or a desktop, that's our 21. And remember, as a check, everything here should sum to 1. That's the way to check your work. All right. And it looks like we have 2 questions that follow. So even if you didn't pause before, pause now and see if you could at least do part D. The most important part of part D is setting up the correct notation. So this is where I say it's super important that you pause and try this on your own. We see desktop. We see laptop. No and or between them. And the most common thing is that students will give me and I give almost no points. If this is a 5-point question on the exam, you're getting 1 point. So totally not a mistake you want to make. No and, but we do have a keyword of given, which means we know they have a desktop. What's the probability they have a laptop? The next mistake I see is I have students a lot who will come over here and they'll grab values from the Venn diagram where it's really easy to make mistakes. Because even if they take the time to translate this using the formula, our conditional formula tells us we should take the and divide by the piece we knew. A lot of students would be able, if they did the Venn diagram, would tell me this is 0.22 divided by 0.31. Because they'd come here, they grab this for D, and they grab that for the and. However, that's incorrect because D is both of these things together. So this is why I caution against using the Venn diagram for anything. Super easy to make mistakes with. Whereas if we're in the contingency table, it's a lot more obvious to say, okay, we want a desktop. Oh, we need to go past these 2 to grab that 0.53. So just wanted to point that out. This is why I'm a big fan of the contingency table to do this work instead of otherwise. Sorry, I'm trying to get you the actual value here. So this is 0.4151. All right, and then our last question here is owning a desktop computer independent of owning a laptop. Remember, we have our 2 methods. Method 1, we could check out the AND formula for independent events. Is this equal to the 2 probabilities multiplied together? So we know that this is 22. Is that the same thing as, what was L? I forgot. 0.48 times that 0.51. So 0.244. And this is where I was saying, statistically, 22% versus 24%, they're not that different. But in part 4, we're really in math land. So is 22 the same as 24? No. So we can say these are not the same. Therefore, L and D are not independent. Or we can just say are dependent. Either way. As I mentioned before, this is the easiest way. However, method 2 is also useful. And that's to use the conditional statement, especially if you really get that understanding of what the hell it means to be independent. This means that knowing something gives us no new information. In this case, knowing desktop gives us nothing new about laptop. So knowing this doesn't matter. So we should have these equal each other. So we know this is 4151 from the previous question. That's why I set it up this way. We know laptop is 48. They're not the same. And now we get an added bonus if we can say, look, they're more likely to own a laptop if they don't already own a desktop, which also makes sense. So they're dependent. And we can even go a little bit further and say because blah, 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 if you own, or a student, it's not you, a student owns desktop, less likely to own a laptop, blah, blah, blah. All right. So that is our testing for independence. And again, this is a question you're going to see on the exam. You have to set up a contingency table, answer at least one probability question, probably two, and then potentially check to see if the two things are independent. And I'm going to give you a heads up here. They're not going to be independent, because if they were, one of the most common mistakes students make of just taking these values and multiplying them to get the intersections would be a correct answer.